Hello everyone, this is a follow-up for my previous video fixing a 16-inch Mac, the one after 2 repair shops and massive water damage. So for now we backed all the data. I also checked the device a little bit more. It seems that we have no audio from the internal speakers and we won't try to address it. So I thought this would be a very nice example of showing the logical analyzer or the analyzer method. So you can use it for many different circuits, many different boards. It's not just for the audio. Basically, anywhere you have some communication lines, in our case this would be E2C line, you can use it to figure out what's happening. So the reason I need it is that there's some soldering happened, I believe at least on one part, maybe on both sides of the board. Each side has 3 of audio amps. So each amp has its different E2C address. So far I see that it looks like they are pre-programmed because they seem to have some narrow compatibility, but it's not 100% clear how compatible they are. So I've seen people reporting that if you replace whole set it will work, if you just swap one chip it won't. But actually I did replace one chip, I believe it was even between M2 and M1 generation, and it was fully compatible. So most likely the compatibility problem is not that bad. Maybe there was something else wrong with the soldering or whatever, so maybe it was a false report. But anyway, so let's go to the schematics. Okay. So the first we're gonna go to the one of audio amps on the left side, just to locate its E2C signal line. As you may see, there are like 2 lanes of E2C signals for left and for the right side. So what we're gonna do is we're gonna listen to the traffic on this line. So to do this we are using logic analyzer. This is Kingst LA2016. It has 16 channels. This is actually quite nice device. The software is also nice. So there are many different devices. You can also buy a cheapest like $5 analyzer. It will also do its job. I bought it because I am trying to do some deeper analysis for what's happening in the board, like startup sequence and so on. So far I didn't really succeed because I actually built some sort of the testing board, but I had to use analyzer somewhere else, so I had to disassemble it. So I only have like the part of the sequence. But basically, for now, it's not really anything new because the sequence is pretty much the same as on M1 platform. So the newers are mostly the same. Okay, we're gonna put the green one, the green cable on the clock and data. So this one would be clock. So basically what we did, we found clock and data signals for the E2C. And the idea of E2C is that each device on E2C bus will respond to its address. And this is exactly what we're going to listen. Okay, so we also need to connect ground. So let me show you how does it look. So we got our logic analyzer here. It has lots of cables here. I did some sort of breakout board with small wires. I'm not sure they are good visible, but they're like just a jumper wires. So I can easily solder up to 16 channels. So this makes diagnostic somewhat easier. So what we're gonna do now is that we're gonna set the thing up to listen to the traffic of the board if we start it, because on the init there will be a ping to all the amps. So we are gonna find which amp is not responding to the ping, if any, because maybe there's something wrong with the reset line. We are also going to test the reset lines. So speaker amp reset L. This is this one. Maybe we'll even connect it. Yeah, we'll actually solder this one as well. Maybe we will use this as trigger to start listening. Alright. So this is the reset line. Let's solder the third wire to it. Okay, so now we have clock, data and reset line. Now let's go and set up LA. Let's go there. So what channels do we need? We need channel 2, channel 3 and channel 4. We don't need channel 5. So this one will be clock, data and reset. Okay, now so we set it to a 1.8 volts CMOS. Oh, so the OBS doesn't show the menu, but you can see here it's 1.8 CMOS. CMOS. Let's remove analyzers. We need E2C. Let's edit. So we have SKL on the second and the SDA on the third one. 7-bit address bits only, so all defaults. Okay, so now let's check. So we are doing 100 mega samples at 5 megahertz. So 20 seconds, it should be fine. It should be more than enough to get the sequence. Okay, so now I'm gonna start this thing because I didn't set up trigger yet. Maybe I won't need it. So now let's connect power. Let's wait till it gets to 20 volts and some power, and now stop. Okay, so we had some traffic here. Actually, maybe I already fixed it. I'm not quite sure because, you know. Okay, so as you may see, there's some communication happening, and only then we have reset signal going up. So here so basically we have two devices answering here. It was 0x9C, 0x8C. Okay, let's check here. There should be 3 of them, I believe. Okay, now let's find the page with square thin lines. Okay, so let's go to let's search it. Let's see if we find any of these addresses. They might be in different number. Okay. There should be a square-C address page. It's not really easy to navigate with Flexport View PDF viewer, because maybe I'm just dumb, but I don't know how to make it show all pages. But this is gonna be fine. Let's hope that square C is not stripped here. Okay, that's not the right one. AP square C connections AP. Okay, this is, by the way, you already notice this is ACE2, so these are CD32 3217. So basically this is the way you can actually figure out which one is missing from the line, but we are going to look for different one, because obviously they reuse the same address on different lines because they are physically isolated from each other, so it's completely fine. Let's look for the page which shows us speaker amps. Okay, so we have one here, so this would be 38, 39 and 3A. ABC. And there should be someone here. Okay, the same page. Okay, so let's just remember it's 38, 39 and 3A. And let's look for other ones, or maybe I will note it. Okay, 38, 39, 3A. Okay, so this would be ABC ones, okay. There should be more, but for some reason I can't find them here. Okay, let's try to decode it a little bit differently. Speaker amp as clock. Let's check how it's called on the CPU. Oh, and by the way, it's 1.2 level. So let's probably change the analyzer and do it once again, because otherwise we probably have wrong readings, just in case. Okay, again, let's restart it. Okay, let's look at the traffic. Okay, so we have 38, 39, and I think we also got 3A. Okay, so this part should be fine. Most likely it's fine. We have same, so we have this reset signal. So we have some communication with the 38, then it goes to the 39, then it goes to 3A. And as you may see, there is AC key. AC key means basically acknowledged. So the idea behind this communication protocol, so it's a little bit more difficult, but basically master sends packets. Each packet has its destination. So if someone receives this destination, at some point it should answer by pulling AC key bit. The way that master understands that, okay, it was received by someone here. So basically it could be the way you can imagine it like that, like I'm saying you every time I'm saying you exactly 7 words, or 7 words, and on the 8th words you should answer me yes or no, or if you understood what I said or no. So every time I communicate with you, I tell you exactly 7 words, then you tell me, okay, I got it, or you just say okay. Or if you don't answer to me, then I assume that you didn't hear me, or maybe I didn't address it well, maybe I misspelled your name. So this is how it basically works. So there are different formats, like you can have different frequency of this line, you can have different bit, you can have different basically you can see all here 7-bit address bits only, you can 8-bit, and so on. There are huge amount of videos and explanation how exactly this line works. If you are interested into programming something by yourself, like building a small analyzer which simply shows you like which addresses were seen on the line, then probably you need to go a little bit deeper, so you decode it by yourself. But basically you can also use just normal plugin, or like it's in almost every single logic analyzer. It's actually built in Future to decode most common lines like SMBus or E2C or whatsoever. So this one you can do SVD, UART, CAN booth, and so on. And mostly you can also download extra. Okay, so now we are going to go to the different site, because it seems to me that this site is working, because all 3 of them did actually answer. So you can actually see it down to bits. You can see how data line is sending some bits and how the acknowledged bit is being issued at the right moment. So if there was one missing, we would never see an AC key bit from the proper address. Okay. So now let's desolder this stuff. So we'll probably keep the reset signal. I'm not sure if the line is long enough. Oh, okay, it just snapped. There's a cap missing here, but whatever. Okay. It seems that it was also soldered here. Not only soldered, there's also some damage I didn't see before. So, like, here's cap missing, I believe. Yeah, most likely this is the cap. Not sure if it's important or not, but we'll figure. Okay, now let's go to the board view. Let's rotate the board as we did here and go there. Okay, let's check what's here. Okay, this is some filtering hub. We can mostly ignore it. I mean that it's doubled. It probably would be nice to have. Yeah, it was definitely soldered here. Okay, but let's find the CLSDA. Okay, so the clock was green. Actually, I just, because the idea maybe they would have the same addresses, because there's no reason to use different E2C addresses. Okay, so clock data green, yellow, and reset should be somewhere nearby. Okay, let's go yellow. And the third bar, it's not that necessary, because yeah, it's actually useless to use a trigger. Interesting, there are like test points for nonce here on this side. Anyway. Okay, there is no reset test point here. It's all on the right side. Whatever, just ignore it, because it's a global reset, but it's so they didn't want a double test point for that, because obviously it's going to reset all speakers at once, not just one. Okay, so let's go back to analyzer and let's hit this record button. Wait till we got to the 20 volts and just a little bit more. Now it should probably play some audio. Now let's stop it. Okay, so maybe I soldered this not properly because it's all garbage here. There's nothing really going on here. Maybe the ground was disconnected. So let's do it again. Yeah, so most likely ground got disconnected, so it just got like some noise shit. Okay, let's record it once again. And stop. And same garbage once again. Oh, okay. Let's check once again if I soldered it properly. So, speaker amp right, SCL. Ah, okay. Where's SDA? Clock? I'm just assumed it was nearby, but it's not. SDA. Ah, okay. So the clock is here and data is here. So for whatever reason they're not paired. Alright, now it should work. Let's record it once again. Where's my cable? Okay. Got 20 volts. It's enough. Okay, now we have much better picture. So we have 38. 38. We have 3C, 3D. Okay, it didn't like something about 38. I'm not quite sure. Okay, we need to do once again. Maybe ground got disconnected on the way. Okay, ignore reset for now. Okay, we have basically similar pattern, but okay, 38, AC key. This is 0x3b. Okay, let's search for it. Okay, here we go. So this is 3B, 3C, and 3D. This would be the left side. Okay, so we have 3B, we have 3C, and we have 3D, and 3D is not acknowledged. Alrighty, so now we have to know which one is the wrong one. So DEF, probably this Tawang F will be the right one. Tawang. Now go figure which one is which on board. So it's definitely gonna be the topmost on the lower, or the lowest one. Okay, Tawang B0. Tawang B0. So there are Tawang B0. Alright. So let's just assume that they are, okay, what I'm doing. Let's just assume that they are placed the way they are. Okay, it should probably be this one, but I'm not sure. It might be, it might not. Okay, so let's remove it and see what's underneath it. Let's put some glue on this cable so it won't go away as we solder it. Okay, so this is quite straightforward matter. So I think we found which one is the third one. The worst thing would be that it's like flipped or not, but most likely that would be it, because we see some water damage here. Probably it wasn't even removed, so probably it has some dirt underneath it, because the caps, they don't look really nice, they're not looking healthy, and they should be replaced as well. Because such caps, it's just a ticking bomb, you know. As I told in previous video, such caps can simply go short circuit all of a sudden. Well, not really all of a sudden. Oh, yeah, there's some dirt under the connector. Oh, it actually looks quite nasty. I hope it survived. So we need to reball it and put again. Or you can simply reball everything and you can simply replace everything. It also works. Because this motto, work smart not hard, is actually a little bit not really true, because sometimes work smart means to work hard, or you just waste way more time, you know, like trying to figure some stuff, some useless stuff, like you will need it maybe once or 2 times in a year, but you waste hours and hours figuring it out. So at least in repair business, it's not entirely true that there's either smart or hard work. It's kind of the mixture all the time. Okay. Enough life coaching. Okay. Okay, I'm not very happy in how it looks. And by the way, never do the thing I did right now. Never solder a chip on the magnetic pad, because the magnet will attract the soldering iron, and unintentionally you will simply scratch it. So don't do this. Okay. Okay, looks clean enough. I have no idea if I have proper stencil or not. You can always take a bigger one, not a big deal. Because these small chips are really absolutely easy and trivial to reball. But I remember times buying LP8550, the backlight on the LED backlight on MacBook Airs, like Intel MacBook Airs. Just to save some time reballing it. But basically you like saved some time, then you had to flash it to get proper brightness control. So it wasn't really that time savory, because you just like moved your time somewhere else. You had to boot Linux after that and use the Pirno, the great. He did a script to adjust to fix the brightness slope of the controller, because you replace this chip with just normal Texas Instruments and it's not really configured, so you have like step or ladder type switching on the backlight instead of the nice slope which was configured by Apple for this chip. So you just need to flash it once again from Linux, or you can simply reball the old one. Up to you. Okay, now let's remove solder, put chip back there. Also, I'm not sure I have caps on my donor board. No, I'm not. So the reason I'm doing all of this is that if one of amps is not answering online, there will be no sound from speakers. So you need all 6 chips answering to get audio. Alright. Okay, let's remove 2 ticking bombs here. Oh, someone changed this cap actually, or not? There are different type caps here, different color. Okay, so now we should have all 3 chips on ESPRC line. Oh, this one got... Oh. I destroyed one of... this one is done. This is like probe, but I have too many of these. Okay, so let's get back to the logic analyzer and let's hit record, plug the cable. Okay, 20 volts, probably in it, stop. Okay, so now we are talking to the 3B, we are talking to the 3C, and we are talking to the 3D. So now this thing should sound. And let's find some caps. Okay. And after that I want to hear it. It's actually kind of like startup sound. It's not as good as a Windows 95 startup sound or the older Mac sound, but it's fine. Okay, this is 10 microfarad, 25 volts. Let's see where we can get such. Okay, no, it's not. I've just got this very similar board here from the 14-inch. I'm trying to scrape it a little bit. Actually, this one wasn't that bad. It has like hole under the Wi-Fi chip. Wi-Fi chip was right, but Wi-Fi solution is there, so I already ordered some stuff for it. So it's incoming, guys. There are so many devices which could be fixed now. I think I will even fix this board, which is unfortunately already has been donated quite a lot. Okay, 16 volts, okay. This one. .2 volts, 50 volts. Right. Maybe near nuns. Here. 10 volts. Okay. Probably here. Okay, yeah, this will do it. Don't want to use hot air here, because this would definitely destroy the connector. So let's just use 2 soldering irons. Okay. Looks nasty. This side is ground, so I need different bigger one. Okay. Yeah. This is all about LA. Okay. So now we can remove our probes. Clean the board. I won't full assemble it yet because there are lots of many things, smaller things to fix here, there are also lots of bad caps here and there which needs to be replaced. But for now, I'm just want to hear the startup sound and call it a day. At least for this board right now. Still looks nice too. I cleaned it so many times here. This is, I believe it's backlight for the keyboard. They still use the very same backlight driver they used for the display and keyboard drivers back then, since 2016. No, it's 2013 actually. So there are literally chips on this board which are 12 years, and the oldest one actually is a 5-volt rack for the left side. This is GRV chip. You can find it even on 2009 MacBooks. You can source it from there if you ever need it. So Apple is really conservative in some like smaller chips. Which is both pro and cons, because like using the very same SSD power IC which they used before, they use it now for 5-volt rail on the right side, and it fails, obviously, killing the right side USB-C port. Just a typical failure. Okay, there are a few caps to replace on this side of the board. This one looks not really nice. Yeah, so I think I will need probably 1 hour to replace some caps. And some people write me even now. I have MacBook to fix, but it's like almost 10 p.m. here. Okay, I forgot to connect the right speaker, but one is enough for now. And there are some other stuff to address here, like the right fan has corroded cable in it. I'm not sure if it was fixing or simply replacing. Would be nice, because I think you can't really order just one. Oh, we got sound. That's great. Once again. That's the sound of the fixed 3D amp. Okay. So that's it for today. I hope that this will be useful, because you can use this E2C sniffing for all types of the repair. Like if you're repairing charging circuit, you can also sniff what's happening here, audio amps and whatsoever. So you can always figure if something is not talking or something is not answering. There are so many E2C lines, like there are E2C lines to the display, to the camera, and so on. So you can also listen to the camera and see if the problem is with the camera itself, with E2C line to it, and so on. So a very powerful tool, actually. Just like $5 or $10 for the very simple analyzer with like 8 or 4 lines, and this is more than enough to analyze this stuff. Okay, so now we are up to the next repairs. Not that interesting repairs, like display fixing and so on.